Let me welcome everybody to our science talk. It's so lovely to see so many faces online. We're happy you could join us tonight for the Noyo Talk Science series. I am Sheila Siemens, the director of the Noyo Center. For those of you who aren't already familiar with me, I'm happy to make your acquaintance. We bring you these series free of charge, but we do encourage you to donate to the Noyo Center and or donate $10 for the talk. It's a really important thing to be doing right now. It's a tough time, as you know, and every little bit helps. So $10 for tonight's talk or any amount you want to give us. We really appreciate anyone who has donated to the Noyo Center in the past or donated recently. Thank you so much. So with that, I am going to introduce Joy Reidenberg. Joy, I was just telling Joy, I was thinking about her on my walk today because she came into our lives before the Noyo Center even existed. The Noyo Center was just a good idea by the city of Fort Bragg that they were interrogating as whether or not something like that could survive. And here we are 17 years later, have an organization that just celebrated its 10th anniversary. And we are about to break ground, amazingly, on the laboratory hopefully this spring, as soon as the weather allows, to put this blue whale skeleton in a home where we can actually start to repair and articulate the skeleton. But way back when Jeff and I met in the belly of a blue whale, Jeff said, we got to send some of these parts to different researchers. And he introduced us to Joy. Joy is a professor at the Icahn School of Medicine at Mount Sinai in New York and has been studying many different animals, but was very excited to get the blue whale hyoid set of bones that make up the blue whale hyoid, and had them for many years, right, Joy? How many years do you think you had them?
I had him since you guys sent it, which was the year the whale stranded, I believe,
Yeah. Well,
2009. And
so
it
you,
sent
yeah,
it back in 2018. So
yeah.
I had it almost 10 years, I
Yeah,
guess.
so you were the custodian of part of our whales, as were other people. We sent away many different parts of the whale, and it's really great to get Joy back, as we have with others, to hear about the research that came out of that and also where it's led her down her career. So, well, help me in welcoming Joy, and we will begin this presentation now. Joy, if you want to start your
Okay, I will do. Before I do, I just have to show off that I'm wearing my Blue Whale Ale shirt, just in, from
oh,
Pacific
very
Coast
nice.
Brewing. I figured it was timely for this.
Oh, very nice.
Excellent. So I couldn't help but choose some alliteration for my title, Bewildered by Betty Blue's Big Basihyal Bone. And I will have to admit that Basihyal is really not the entire bone. Basihyal is just the main part of the bone. But we'll go over all of that. So if I just said hyoid bone, it wouldn't fit my alliteration. So I'm going to focus a little more on the Basihyal. But before I do that, um, you should all know that I'm at a medical school, and that means that our focus is usually on humans. Now, when we focus on humans, of course, if I do something on whales, people look at me kind of sideways and go, "What are you doing?" It's like you're at a medical school. You should be looking at people. And I think the important thing to understand here is that even though many people who do research on animals are focused on people, their research is looking at animal models of people. So you can test a new drug or a new surgical procedure or whatever, because they're looking at animals that mimic people. We, on the other hand, are the weird animal lab. We're looking at everything that is the farthest we can get from people. And the reason for that is we want to be inspired by nature to help come up with new solutions for people problems, whether that's a new type of treatment for a disease that mimics that extreme environment, or protective devices for people who want to live or work in those environments, or perhaps even new technologies to do things like, I don't know, underwater communication or better mobility systems and so on in certain environments. So that's what we're interested in. What are animals doing that we can learn from? And so the weirder the animal, the more interested I am. And that, of course, brings me to whales, even though I work in New York City, where it is really hard to work on a whale in the middle of Manhattan, at a medical school, which is not really geared toward looking at animals. But I do it because I'm hoping that we're going to learn some really cool things from it and apply it back. So I'm going to show you what we've learned from this whale. So let's see if I can get this. Okay, there we go. So before I go into Betty Blue's Basihyal bone, I have to really explain to you what a hyoid bone is. So a hyoid bone is this little tiny U-shaped bone. If you make a U between your finger, your thumb and your forefinger, it's smaller than that. Okay, it's a little tiny bone. And if you take your hand and you put it up to your throat, above your Adam's apple, and sort of look like, like you're trying to choke yourself, that's approximately where that bone's going to be, where the flat part of the floor of your mouth meets the vertical part of the front of your neck, right in that little junction. That's where this little bone is. And because it's in a critical location, it supports the base of the tongue. It pulls on the front of the jaw. It helps with elevating the larynx or voice box. And so, therefore, it's at the intersection of both the breathing and the swallowing pathways, and it has functions in all of those areas. It helps widen the gape, it helps in chewing, it helps in swallowing, it helps in breathing, and of course, it helps even in sound production because it regulates the position of that larynx or voice box. So if we look at a diagram showing the various muscles attached to this bone, we realize this bone, which is located right here where that little blue circle is, actually has a lot of muscles attached to it. Most of them are either just above or just below it, but there are a few going out of the plane of this diagram, away from you and into that plane that go up towards the back of the skull. So there's a whole bunch of muscles that are pulling and pushing on this hyoid bone in different directions. So depending on where it gets pulled, different functions happen. So we think of this hyoid bone as like a hitching post for the muscles that go to the jaw, that go to the tongue, that go to the skull, that go to the throat, that go to the voice box, that go to the chest, and even go to the shoulder. Isn't that crazy? These muscles go even to the shoulder. And when we look at the hyoid bone of a human, it's really comprised of two major parts. The part in purple is the basihyal part, so it's the middle part of the bone. And the part in orange is called the thyrohyal. So they're like wings on either side. And thyros means shield. So they help make a shield going around the side of this hyoid bone. The little tiny horns in green are called the lesser horns, and they simply connect that hyoid bone with a ligament up to something in that diagram that's labeled as ST, which is the styloid process coming out of the back of the skull. So humans have a ligament, a stretchy little rubber band-like string that holds the hyoid on either side to each of those two little green bumps. And therefore, it's free floating in the neck. So it's not anchored to any other bone. It's the only bone in our body that's not anchored directly to another bone. It's just free floating in that area, held on by these two little rubber band-like strings and lots of muscles pulling and pushing it all around. So that makes it a really unique bone. So these are all the different directions for each of the different muscles that attach to that hyoid bone. So you can see how many things attach and how many directions it pulls, even including, I don't know if you guys can see my pointer. Can you? I hope you can. Even this one over here, which is going off to the shoulder. So it's kind of crazy when you think about that. Let's look at other animals because this is not a uniquely human trait. So this is a mid-sagittal cut of a pig's head. And in the very center of this illustration, well, it's not an illustration, this photograph, in the very center here is where the hyoid bone is. Here is the voice box over here. This is the tongue over here. Here's the brain up here. Here is the nose over here. And all of those different directions coming out from that hyoid are indicating all the different muscles that pull it in the different directions it can go. So it's a really important bone, even though it's pretty small. And that bone takes on lots of different shapes in lots of different animals. You can see the human in the bottom there, that U shape. And you can see really tiny ones like from a rat, all the way up to really big ones like from the sheep. So there's lots of things going on. Now, what's interesting about most of these bones is that, unlike the human, that ligamentous attachment becomes a chain of bones in most other animals. So if we look at the sheep, for example, the biggest parts of the sheep bone are actually the parts that in us are just that rubber band of ligament. The U-shaped part is actually a smaller part of the bone. And that tells you something about its function and constraints on its movements because that rubber band ligament is not able to stretch if it's now made out of bones. And so they have a much more constrained excursion of that bone as it swings back and forth in the throat. it's not going to have as much range of motion as a human one will, which is not constrained by the bony attachments. Here, for example, is what it would look like in cattle. And by the way, I use the word cattle and not cow. People sometimes interchange them, and they're not, because cow is just the female and bull is the male. So unless you really just mean the female, we should be calling them cattle. So this is cattle. And in cattle, we see the orange and purple parts, which is the same as a human. Okay. You've got the basihyal in purple and the thyrohyals in orange. And then you've got all those other ones, which I won't bother telling you the names of because it's just a lot of anatomy jargon. But you can see that the blue one there is actually quite large. It's larger than the whole rest of the hyoid, which means that that's the most important part of this. That's where most of the muscles in this animal are pulling it back and forth. And it regulates a little bit the movements of the head and the jaw and the larynx, but not to the same degree of excursion because it's fixed to the base of the skull. And you can see how that purple goes to the little bit of red, which then goes right into the skull. And so with a chain of bones like that, there's very little excursion. So it can swing back and forth, but it can't really rise very far down, very far up and down like it can in a human. Here's what it looks like in a horse. So this is a mid-sagittal cut of a horse, and we've dissected away everything on the side so you can see the bony attachments of that hyoid apparatus all the way up to the base of the skull. So I hope you can see my arrow. Right now I'm showing you where the brain would be, which is in here. And then coming out of the bottom of the skull right here, all of this is part of the hyoid apparatus, this part here. So you got this little bone here, a big long one here, another one over here, another one over here, another one here. And then we get into the larynx itself. So this part over here is similar to what humans have, and all of this here in us is simply a stretchy ligament. If we take away the whole rest of the horse's head except this part, you can get a better idea of what that hyoid apparatus looks like relative to the rest of the voice box or larynx. So we've got this part up here, which is the part connecting to the skull, this part over here, which is similar to what humans have, and then all of this is the voice box going into the trachea over here. If we look at this diagram of horse anatomy, I've colored in a few things that I think are important. These are the muscles that help regulate that position of the hyoid. You can see how much of the front of the neck is involved in moving that tiny little bone. So we've got this green one over here, followed by a blue one, followed by a purple one. These three are all pulling downward. And then we've got all these red ones, which they didn't put in their diagram, but I'm letting you know they are there. They do attach, and they do go to the different parts of the face of the horse and the jaw and the skull. And that's what all of these other attachments indicate. So this hyoid is stuck between the muscles in the neck that pull it backwards and the muscles in the head that pull it forwards. Now, when you have an animal with a really long neck, as you do in these animals, these examples here of cattle, zebra, camel, and giraffe, having a really long neck means that you need to have the kinds of muscles that can help pull that neck down so the animal can graze or drink. So these hyoid muscles that are in the front of the neck are responsible for pulling that head down. Some muscles act on the neck itself, on the neck bones, but a lot of the leverage is coming from the farthest away you can get from the chest, and that would be coming from the tip of the front of the jaw. And if you go with muscles from the front of the jaw to the hyoid and then to the chest where the breastbone is or sternum, you've got a nice sling of musculature that can pull that head down. Now, it needs to be strong and powerful musculature because on the other side of the neck is something called the nuchal ligament, which is a really elastic ligament that helps spring the neck back up again. So these animals actually don't use muscular energy to lift their head back up again. That happens naturally as that elastic ligament recoils. And it's a very, very strong ligament, and it's very thick. So they need very strong muscles to pull their head down to feed. And then when they want to relax and walk around and not have their head drooping on the floor, they simply let go and relax the muscles, and up rises the head. And that's why giraffes can walk around and save energy with their head high in the air, because they're not using energy to keep it up there. They're using the elasticity of that ligament to hold it back. But what happens if you don't have a neck? And that's where we have a really interesting situation in whales, because when you look at a whale, they really just go from head to chest. There are neck bones in there, but they're highly compressed, and we're going to see some of them later. But essentially, they go from head to chest. There's no long neck here. So if there's no long neck in a cetacean, in a whale or a dolphin or a porpoise, then we expect there to be a much smaller hyoid and much smaller muscles because they don't need to pull their head down. So this is what we're expecting. Let's see what we actually see. So when we compare the human and cattle and we look at a cetacean, all of a sudden we see something bizarrely uncalled for. We're expecting a little tiny hyoid because there's no neck. And in fact, it's a humongously big hyoid. And you can see again the equivalent parts for homology, the purple part being the basihyal, the two orange parts being the thyrohyals, and they comprise a boomerang shaped or U shaped hyoid, which is similar to the human. And then there's those other parts that are shown in green, pink, and purple, and a little bit of red, which correspond to the same things that you see in cattle. So, and most other animals. So there is a connection, at least in toothed whales. That is the dolphins, the porpoises, the sperm whales, the beach whales. And this connection means that there is some constraint on how far this hyoid can move. But it is important to note that the surface area of the purple and orange parts is so large because that means that there's a lot of musculature here. Now, if there is no neck, essentially, why does it need such large musculature? Well, it's thought that most of this is because depressing the hyoid or pulling it back towards the chest pulls the tongue back. And by retracting the tongue back very rapidly, you can create negative pressure inside the mouth, and that creates suction feeding, which is very important for toothed whales. So let's take a look at a toothed whale. This is a dolphin that's been cut in the midline, and here's its hyoid bone. And you can see that it lies at the junction between the larynx, which is this goosebeak shaped thing over here. Here's the trachea, here's the larynx, and the tongue, which is filling the oral cavity up here in front of it. Okay, I hope you can see that arrow. So as this hyoid is pulled towards the chest by this big bundle of muscles, see this big set of red muscles here, this would connect to the breastbone or sternum. And as it pulls the hyoid backwards, it retracts the tongue back. So the tongue is acting like a piston. Now, here's what isolated hyoid bones look like. And these happen to be from a pilot whale. And we're looking at it in 3 different views, just so you can get sort of the overall shape of what these bones look like. The one on top is a dorsal ventral view. So you're looking at it from above, looking downwards at it. And you can see that the basihyal and thyrohyal parts make a boomerang shape. If we look at it from in front, if you were at the tongue looking backwards at the hyoid, then you get the middle picture view. And you can see it's kind of flat in that position, but all of that surface area, again, is still holding muscles above it and below it. And then the inferior picture is showing you a left lateral view. So you can see from the side how long that hyoid is from front to back. It's pretty long. Now, the hyoid is actually a large bone relative to the skull when you compare it to humans. In humans, it's a tiny little nothing, even though it has a lot of really important functions. It's not a very big bone. It's just sitting at the junction of a lot of different things and can be pulled in a lot of different directions. But it's really, really big when we look at whales. So here's the hyoid in a killer whale or orca. Here's the hyoid in a sperm whale. And I understand you guys just got done dissecting a sperm whale today, so kudos to you. That's a tough job, I know. And this is what it looks like in a gray whale. So that hyoid relative to the skull is a really big bone. Now, let's also remember that the skulls of whales are really big relative to the rest of their body. So we've got a really big skull to begin with, and then we've got a bone that even just in proportion to the skull is a really big bone, which means in proportion to the rest of the body, it's an enormously big bone. Interestingly, large hyoids are seen in fossil whales. So if we look back at something like Durodon, for example, the Basilosauridae, you will see a hyoid bone that's relatively big. And that's big relative not only to the head, but it's big relative to the size of the animal. So as we look at that hyoid bone, and here you can see the whole skeleton of the animal. If we measure that hyoid bone, it's suddenly becoming about the length of one of the shorter ribs. That's how big this is. That's huge. If we looked at our smallest ribs, it would still be about 3 or 4 times the length of our hyoid bone in a human. So compared to us, this is a really, really big bone. So if this bone developed really early in cetacean evolution, before all of their unique respiratory and digestive constraints, then it must have had a function that's not related to the respiratory and digestive constraints. So having a really big hyoid might not have been started by the need for piston-like action of the tongue or opening up the throat really big, the way baleen whales do to engulf their prey, or anything to do with phonation, about elevating the larynx up so that the animals can send air up into the nose so that they can do echolocation. So none of the echolocation has happened yet. The blowhole's not all the way to the top of the head, so the blowhole is over here right now. So we're not talking about an echolocating animal. We look at the teeth, and it's a heterodont. It's got all different kinds of teeth in here. It's not like a regular tooth whale where they're all the same. So likely they're processing their food with these teeth because they have little bumps on the teeth, which means they weren't doing suction feeding, and for sure they weren't doing engulfment with throat pleats. So we know that this hyoid bone has no function in those actions, even though we associate it with those actions today in modern whales. Those are probably overlays on the hyoid today. So where do you find a hyoid? Well, I know we're not looking at a blue whale, we're looking at a humpback. That's okay. That's mostly what we get around here in New York. So that's what I use usually for my diagrams. So the hyoid is located pretty much right there. And in order to find it when you're dissecting into a whale, you want to go halfway between the eye and the beginning of the flipper. And that's roughly where it's going to be located. Okay, and then we have your blue whale. So here's Betty after she's blown up a little bit, lying there. And you see this one guy on the cliff? I don't know who that is. I hope you're watching this show. But he is basically the first fly on the beached whale, saying dibs. And this is me being the first fly on a beached whale. Well, actually, it's not so much a beached whale. It's a whale that died being struck by a ship. It was towed into the harbor and then put up on a dry dock at the Army Corps of Engineers station. And that's where we're doing our dissecting because it's a nice, convenient area. We can keep the public away. We don't have to worry about the tide coming in or the sun going down or where to go to the bathroom because there is a building nearby, or having the help of a lot of heavy machinery. And you can see lots of people wearing hard hats because we're going to have cranes over our heads in a minute. But I point out to you, I'm sorry, I point out to you that this person in the middle with the red hat, that's me. I am kneeling on the hyoid bone. That's what I'm trying to get out, what I'm kneeling on right here. I'm trying to remove all this muscle that's in front so I can get down to the larynx, which is here, and the hyoid bone, which is here. My other foot is standing on the joint of the lower jaw where it meets the skull. And this tool over here, that's my scalpel. So those of you who've been doing dissecting for Noyo, you probably already know about these. These are flensing knives. They look like a big hockey stick with a blade on the end of it. And this is what it looks like when you're pulling the hyoid and larynx out of a whale. So that's me. I'm wearing a hard hat because above me is a very big crane. And right immediately above my head, right there, is the hyoid bone, which is being held by a chain that's going up to the top of the picture and going up to the crane. And they are pulling on that as I am trying to cut it away. So this is how we're getting the hyoid out of the whale. Now, when you have the advantage of having heavy machinery, it makes the job a lot easier, which is why these pictures are wonderful in my view, because it's an easier job to do. When you're just playing tug of war with a bunch of people in a rope on the beach, it's a much harder job to get this out. And so I appreciate how much work went into getting the Noyo blue whale hyoid bone to me, because Betty was stuck in a very awkward place and people had to bring things up a cliff before they could get to the heavy machinery. So a lot of it was just people working by hand and pulling on ropes. And I know how hard that is. And I want to tell you thank you right now for all the work that you guys put into getting that bone to me. This is me working on a blue whale, but one on the East Coast. This blue whale was hit by a ship and came into Rhode Island near Newport, in that area. And you get an idea of just how big this structure is. So this is the hyoid and larynx. Most of what you're seeing is larynx. The hyoid bone itself is kind of stuck between the very front part of this apparatus that's it's coming from the crane here, where it's got like this thumb part and the bucket over here. Where it pinches together is roughly where the hyoid is, right in there. The rest of this is going down to the trachea, is all larynx. And yes, I did fit it in my car, in case you're wondering. It had to be broken into 6 pieces. And actually, it went into 2 cars to get it back to Mount Sinai. And we did finish dissecting it at Mount Sinai. But it really tested the limits of what we could put in our lab, because we couldn't do anything else when we had this thing in our lab. It took up all of our space. Here is a much smaller specimen, so it's easier to get a nice view of the whole respiratory region. This is from a minke whale. And in this minke whale, you can see at the very top of the image is the hyoid bone, and it's kind of been partially dissected out here. So you can see this boomerang-shaped bone right there. And this sort of gray-green musculature has been pulled away from it. The rest of it that's in a little bit better shape, that's pink, all of this is larynx, shown in that yellow bracket. Here's the trachea, which is underneath part of the larynx, and then it bifurcates into the 2 main stem bronchi. And then we have one of the lungs outlined in a bracket here. The other lung obviously is on the other side. And you get an idea here of just how big the sound production apparatus is in a whale, because we've got a larynx or voice box that is approximately the same size as a lung. Now imagine if you had your larynx the size of your lung. It would be hanging off the front of your neck down halfway down your chest, because it would be such a large organ. And we have a neck. Whales don't even have a neck. So with that compression of the neck region, this larynx is actually occupying the beginning of the chest. So it's a very large organ. And here is your Betty Blue. Here's what it looked like as it was all blown up with gas. Okay, it's lying on its back. Here are the throat plates that are expanded. The eye is approximately over here somewhere. These are the baleen plates. This is the upper jaw. This is the lower jaw, got stuck on a rock up here like that. So, and this is a flipper. So hopefully you're all oriented. It's lying on its back. Here it is, I guess a few hours later, as this part where the throat pleats are has been cut, and folks are cutting away in here. Thank you to all of you who got nice and messy, including you who ripped your pants here, I see. But by cutting all of this away, enabled you to get down to where the hyoid was. And so the next picture in sequence, we're looking here at someone who's retracting back the hyoid bone. Dare I say that might be JJ? I'm not sure. I can't tell. But here's the hyoid bone being pulled back away from the rest of the larynx, which is over here. And here, the whole hyoid and larynx were pulled out. And this lovely lady here is showing us the length of that larynx. And you can see with a centimeter scale here how big that larynx is. And the hyoid is over in this area here. And here's where it was dissected away. And lots of great pictures were taken of that larynx. So I did not get the larynx. I only got the hyoid, but I got all the great pictures from it. So I have a pretty good idea of what that anatomy looked like. This is actually what arrived. And this is after I unboxed it. I have to tell you, it was very funny. It arrived when I wasn't home. My husband was home, working from home. And 2 big burly guys from, I think it was FedEx or UPS, I'm not sure which, carried the box, which was a refrigerator box that had been peeled open flat and then rolled around this hyoid and taped shut again. So it became sort of like a disfigured cylinder. And 2 guys were carrying this thing to our house, and they asked my husband, "What is in here?" And he said, "Well, why don't you guess?" So guess what they guessed? They said, "It's Longhorns for your Prius." So yeah, we had a little Prius, and just the idea of Longhorns sitting on the front of our Prius just completely cracks me up. And every time I see this hyoid bone, I keep thinking it's basically Longhorns. That's what we're looking at here. So this is the hyoid. It came in 2 pieces. We've got the big boomerang shaped part over here, which I'm going to show you the anatomy of soon. And then we got these little smaller pieces that help hold it up to the skull. Okay, here's what it looks like after we cleaned all the flesh off of it. And I put a little human hyoid bone on the box in front, so you can see the human compared to the whale. Now, obviously, humans are smaller than whales, so yeah, it's going to be smaller. But remember, it's also smaller relative to the size of the head. So we're looking at the hyoid basically from below. If you were under the whale looking up at it, swimming over you, this is the view you would have. This part over here, which still has a little bit of oil on it, is the Basihyal part. These extensions on either side that look kind of like lovely little thighs, okay, little chicken drum bones here, or whatever they are. These are actually the thyrohyals. So they're the extensions, the wings to the side. And then on top, these two club-shaped things are the equivalent of what was the blue bone in cattle that was holding up to the skull. But the big difference here is that this bone is still free floating. It is not attached physically to the basihyal, and it is not attached physically to the skull except through very stretchy ligaments, which means that even though there is a bone on either side that helps to stiffen that connection, there's still an awful lot of stretchability, an awful lot of flexibility in where this bone can go, because they're not rigidly constrained by a series of bones that are jointed to each other. Again, here's another cleaned up version without all the boxes and distraction in the back. Looking at that hyoid as if you were looking from below at it. And you can see the little human hyoid bone in the front here at the very bottom. This is a view from the side. And we've tried to articulate those two bones that connect to the skull as close as we can, but they are physically not touching. They're actually separated here in the front. And then this is what it would look like if you were in the tongue looking backward at the hyoid. Again, we've got those two smaller bones that hook up to the skull, but you see a very big gap between the end of this bone and the beginning of this bone where there would be a ligamentous connection. By the way, there's also cartilage here and here, and then there's a ligament in between them. Here is us in the lab measuring. This is my colleague, Jeff Laitman, and he's helping to measure one of the hyoid bones. This happens to be from a humpback whale. You can see it's a lot smaller than the blue whale. And so we're getting all of our measurements simply the old-fashioned way with a tape measure. And here's a whole bunch of other whales just for comparison. We've got the blue whale on the top left, the minke whale on the top right, the fin whale on the bottom left, and the humpback whale on the bottom right. And they're all oriented the same way. And what we can see is they pretty much have a very similar shape. Some are a little more sharp in their V shape, some are more gentle in their curvature, but there's a lot of similarities in the shapes of these bones across the different species. Here's looking at them from below. Again, there are a few species-specific differences, but there's a lot of similarities. The basihyal is the center part. The two thyrohyals stick out to either side. And all of the baleen whales have two projections going forward towards the tongue and two smaller projections going backwards towards the sternum or breastbone. This is us dissecting the hyoid that came from Betty. And this is after we had it sitting in the backyard composting for 6 months. I really wanted it to compost because I wanted to see the bone itself. There was nothing really useful on the flesh that was all cut away. So I just wanted it to melt off. And guess what? It didn't melt off. The muscle all melted off, but I don't know if you can see it, but the way this outer sheath has been pulled back, and you see how it's been pulled back here and pulled back over here. This sheath has a really, really thick cross-section right over here, right above the tools in the midline. That really thick cross-section tells me that this sheath covering the bone doesn't decompose very easily. After 6 months, it was still there. And I can see why cleaning off the bones of this whale could be really difficult. Even after years of being in the ground, everything might not fall off right away because there's some really, really thick connective tissue around some of these bones. And the thickness of the connective tissue speaks to how important the muscular attachments are. So in some places, like over here, the connection is very thin. Here you can see the cross-section. It's very thin where it's been cut right there. In other places, it's extraordinarily thick. So essentially in the midline where the basihyal bone is, the connections are incredibly strong. That tells us that the muscles that pull on it are incredibly strong because the muscles are attaching to that sheath, which is wrapped around the hyoid. And most of the muscles are in that midline, the ones that are very strong. The ones out to the side, less so. So here's some close-ups of that same covering. Okay, so here we're looking at the front of the hyoid going up towards the tongue. Here's where it's been cut away, and you can see bone on the left side of the left image, and you can see the sheath on the right side with the black outer covering and the white area where the cross-section is. Look at how thick that is. If any of you have ever held a scalpel, you get an idea of size here from the scalpel blade. This is thicker than a scalpel blade. So it's a very, very thick covering. And here we've peeled a little bit more away from the bone, so we can now see both of the projections going forward towards the tongue on the right side. And underneath where we've pulled it down, that thick covering extends the whole length of the basihyal and into part of the thyrohyal, all along the back edge of this bone, where it's going to connect towards the sternum or breastbone. So look at that. That's the thickness of that covering right there. Very, very, very thick cover. And now we're trying to peel the entire thing off. So now the bone has sort of been lifted upward, and we can see just the sheath. We've pulled off the sheath, and except for where I've cut it and destroyed it over here, the rest of the sheath is pretty intact because it's a really thick sheath. It's thickest in the midline. And that makes sense because that's where the strongest muscles are that are pulling it back towards the sternum. This is just to show you that this is not unique to the blue whale. We see it in all the baleen whales. Here, for example, and not only in adult whales, also in babies. So this is a juvenile humpback. And as we peel the covering off of this bone, here in the top it's covered. In the middle, you can see a slice in the midline where we've cut the sheath. And in the bottom, there's that same slice. And here's the sheath pulled down on either side. And here you see the bone nice and clean because the sheath has been pulled off. A little bit of cartilage on the end over here. And again, it's really, really thick in the middle. Mostly in that area right there. And here's a close-up of that so you can see it. We did some close-up analysis of the tissue, and it's mostly connective tissue, which is a good substrate for muscles to attach to and pull on. And then we noticed that there are some projections on the hyoid. There are two projections going up up in this diagram, but forward in the whale towards the tongue, and two projections going backward or down in this diagram, going towards the sternum or breastbone. Those projections could be reinforcement for the shape of the bone so it doesn't crack, but most likely it's extra surface area for even more muscular attachment on it. So now, that hyoid would be located where that yellow oval is in this diagram, which is a side view of a whale. And you can see the yellow arrow going forward to the chin and the yellow arrow going backwards towards the sternum. The blue indicates the digestive tract. The red indicates the respiratory tract. So hyoid depression can lower the jaw. It can widen the food pathway. It can expand the throat plates. And hyoid elevation can raise the voice box, separate the respiratory and digestive tracts by pushing the larynx up into the nasal region. And it can also help to collapse throat pleats when the whale is feeding. If we look at an animal as it's swimming, here, for example, a baby dolphin, you can see the projection through the bottom of the throat region of that hyoid bone. See how it's sticking out there. And we also see it in this breaching minke whale, because its head is pulled upward a little bit. You can see where the hyoid is sticking out. So the point of maximal protrusion there, the Adam's apple, if you will, on these whales, is really not the same as our Adam's apple, which is our voice box. It's the bone itself, which is just in front of the voice box. That's where the hyoid is. And from that hyoid, we have it forming the vertex for two vectors, one between the chin and the other to the chest. So those are the two main directions that the hyoid is pulled. Let's take a look at some dissections to see where that hyoid is located and how many muscles are really attaching to it. So we took a fetal pilot whale, and that's what you see in the oval on the extreme right there. Turn it upside down. So we're looking at the ventral area or the floor of the mouth region, pulled away the tissues from the floor of the mouth, and peeled back some of the muscles so that we can see the hyoid. So in the photo on your left, right in here where I'm trying to point, hopefully you can see my pointer, that's the hyoid, that's the boomerang part. And you see the same thing in the diagram. So if it's easier to follow a diagram, look to your right. The purple is the basihyal, the orange is the thyrohyal, and the hyoid is shown up above as well. So you can see what that whole apparatus looks like, but it's flipped in that sense. It's flipped the other way around as if you're looking at it from above. But in the diagram that shows all the muscles, you're looking at it from below. So we flip the boomerang upside down because you're looking at it from below now. And you can see how many muscles are attached in there. And I want to draw your attention to just a few of these muscles, even though there are lots and lots of muscles in here. So I want you to see that there's one called the mylohyoid. And don't worry about the names. I'll say them in case you know the anatomy, but don't worry about it. It's basically the muscle that straps across the floor of the mouth like a hammock. And in this case, it's been pulled off to one side. That mylohyoid, because it has the name hyoid in the name of the muscle, means it attaches to the hyoid. And this muscle also attaches to the lower jaw all the way on either side. So when this muscle contracts from the left and right sides, it pulls up the hyoid. Then there's another one called geniohyoid, shown here in the blue. Genion means to bend, like a knee, like to genuflex in prayer. So the geniohyoid is going from the hyoid to the knee of the jaw. In other words, the bend of the jaw at the very front. And we see that that's basically pulling in a straight line, pulling the hyoid forward. Or if the hyoid is stabilized, pulling the jaw down to open the mouth. Then there's another one on the side called the digastric. This one actually does attach to the hyoid, even though it doesn't have hyoid in its name. It's called digastric because in humans it has di or two bellies. In whales, it's technically really a monogastric. It only has one belly, but it's a really big muscle. And it pulls the hyoid laterally towards the sides, again, towards the jaw. So if you have one on either side, it can help elevate that hyoid back up towards the skull. If you're trying to pull the jaw open, then all you have to do is pull the hyoid back, and then these muscles are then pulled with the hyoid, and that helps to open the jaw. So they're either jaw openers, or if the jaw is held closed, they can help lift the floor of the mouth up, and that will help push the larynx up towards the nose. But if they're pulled down, they can create that piston-like action that pulls the tongue back. So how would you pull it down? That's this muscle over here called sternohyoid, which is the purple one, pulling from the hyoid down to the sternum or breastbone. On one side, it's been reflected. You can see that. The other side is still intact. There's another one, I'm not going to go into the details, that has a T on it there that also pulls the hyoid back towards the larynx, and one below that that pulls that muscle and its attachment even further back to the breastbone. So it kind of duplicates what the sternohyoid does, but it's a little deeper in. So there's actually quite a bit of musculature pulling that hyoid backwards. So we see that hyoid as a hitching post in a sling of muscles going forward and backwards. Let's take a look at it from the side. In this case, we're looking at a beluga whale. And in case you've never seen one, there's me examining the throat of a beluga whale up on top there at the Mystic Aquarium in Connecticut. In this diagram, we've shown on the left side the hyoid bones all colored. All the rest of the muscles are not colored. And we're looking at it in a lateral view. So you can see how it's embedded in all these different muscles of that area. It's quite a complicated mess. In the right diagram, we've cut the head in the midline to show you where the voice box is. That's the thing that looks like a goose lying on its back with its beak poking up towards the skull. That's the voice box. And just in front of it, you can see the purple of the hyoid bone. The white space above that is the swallowing passageway. And all of the stripy stuff that's above the letter H, that's all the tongue in that area there. So we've got this hyoid sort of meshed in between the tongue and the voice box, as well as going down to the sternum. So let's take a look at some of those muscles. So we start with the same red one that we saw on the pilot whale. This muscle, we're seeing it in cross section. It's coming out towards you and into the screen, going back and forth that way from left to right. That's the mylohyoid. And when it contracts the left and right sides, it can help elevate that hyoid up or help bring the jaw down. Then we've got the one in blue, which is the same one we saw in the pilot whale, the geniohyoid, which is pulling from the genion or the chin towards the hyoid in a straight line. I can't show you the digastric in this because it's too far to the sides, but there is a pink one in there as well. But now we go on to the sternohyoid, which is that really massive purple one that's pulling the hyoid apparatus back down towards the chest, towards the sternum. So what about a blue whale or any baleen whale for that matter? How does it open its mouth? Well, on the top left, you can see a blue whale feeding. I've turned the picture a little bit. but obviously it would be on its side there. And you can see its mouth is open as it's feeding, and the throat pleats are starting to expand. So how does that happen? Well, it can simply fill its mouth with water, and the pressure of the water in the mouth will help open it. But it has to start by opening the mouth in order to get the water in. That initial opening of the mouth happens by contracting this muscle in red, which is that geniohyoid, excuse me, that's the mylohyoid, and this muscle in blue, which is the geniohyoid that we saw in the previous diagrams. They pull the chin downwards. And then we've got the digastric muscles, which are on the side of that. So we have everything pulling in that direction, and that would pull the jaw down. So now let's imagine the jaw is pulled down like that. Then we've got our big sternohyoid muscle. That's the purple muscle, which draws the hyoid backwards. And as the hyoid is drawn backwards, the floor of the mouth is expanded a little bit further. Then the whole floor of the mouth can expand tremendously as water rushes into that open mouth. Relaxing the muscles allows the dilation of all of those throat pleats, and the floor of the mouth expands tremendously in that direction. Excuse me. Contraction is simply pulling everything back in the other directions. So we're pulling everything backwards to reposition it the way it was before. Now, the jaw itself is raised by the masticatory muscles. That means the chewing muscles in us. Whales don't chew, but they're the same muscles. And the biggest of those is the temporalis. So this muscle is the one that you feel on the sides of your head when you open and close your jaw, like the temple area of your skin on your face goes in and out. That's temporalis there. By the way, here's a fun little fact. It's called temporalis because this is where you show the temporal passage of time. Temporal means time, right? The passage of time is shown on the side of your head because that's where graying usually occurs first in older people. So that's why it's called the temples. It's the part where you show time. Fun little fact for you. Okay. But contracting the floor of the mouth is simply from all of those muscles attached to the hyoid, bringing those throat pleats back in. You can raise the jaw, but that's not enough to push all the water out of that throat area past the baleen. That means you have to pull the tongue and the floor of the mouth up, and that's these muscles that are doing all of that work. If everything is relaxed, that allows that throat pleat area to expand. And expansion of that throat pleat area is important during sound production as well as feeding, because in sound production, air is going into this big bag-like sac of the larynx. And as air is going into that sac, sound vibrations are made, and then vibrations probably from the wall of that sac are then transmitted to the overlying throat plates and eventually into water. That's a whole nother talk on sound production. We can do that another day. But for right now, suffice it to say that the throat plates have to be relaxed in order for sound production to happen. So we don't see whales making sound with their mouth open with any of this tensed. It's usually the mouth closed, but the muscles are relaxed. And then the throat plates can expand and allow these pulses of low frequency sound to get into the water, which is what we're seeing in this diagram over here. Okay, so if the hyoid is important in opening the mouth and allowing the throat plates to expand like this, okay, what is allowing these, why does the hyoid have to be so large? Because it doesn't seem like this is such a big job, because most of the expansion is happening as the whale swims forward and it fills with water. So let's take a look at understanding where the hyoid is. And we know that it does pull back and out of the way to help relax and pull down the floor of the mouth. What's going on in these reconstructions? Now, I picked these on purpose because I understand that cetacea contracting is going to be helping you with articulating the blue whale bones. And I wanted to take a look at some of their articulations and offer a little suggestion that if you do articulate your blue whale with the mouth open, you might want to make a change to where the hyoid is, because it's not in the correct position for a whale with its mouth open. Okay, there's the hyoid, and there's the hyoid again. And here's another view from the front where the hyoid is, and over here. But the hyoid is not lowered enough to create a nice straight line between the tip of the jaw and the sternum. It's actually in this position, the floor of the mouth would indent back up to the hyoid and then come back down to the sternum. So if you're going to reconstruct the blue whale with its mouth open, keep in mind that the hyoid must be in a lower position. Here's a diagram kind of in that same orientation as the previous one where you're looking from below, and we're just looking at a couple of the muscles attaching that hyoid. So if the jaw is held closed because the temporalis muscle is contracted, then you've got this tense line going from the tip of the jaw to the hyoid to the sternum. So we've got a nice tense line. If the mouth is open, all of that's going to be lowered. All right. And then we're looking also on the right side, we're looking from below, and we see again, the blue is the geniohyoid. The light blue on the side would be the digastric muscles and the mylohyoid. And the purple is the sternohyoid, pulling it back towards the sternum. But let's take into account the fact that the blue whale's head is about a third to a quarter of the body length of the whale. So a bigger head has a bigger effect in generating a body wave. So let's turn this around and let's put it on top of the skeleton. This is the skeleton from the blue whale in Santa Cruz. And we can see roughly what we're talking about. So this is the area we're focusing in on. Look at how big that head is relative to the size of the whale. It's a really large head. So that means the musculature on the back that attaches the skull to the vertebra of the back can be pretty strong and pull the head upwards. But the musculature on the other side is not very strong, pulling the head downward. That has to happen from the point of the front of the jaw all the way back to the sternum. So pulling the head up, as this humpback whale is doing when it's feeding and creating an arch in its back, is easily accomplished by the very strong muscles on the back of the head that go to the bones of the spine. Those muscles are very robust. The other side, they're not robust at all. On the undersurface of the spine, we have very, very weak muscles in whales. Now let's talk about what's happening as this whale is swimming. Can the hyoid have an effect on moving that head? We just saw that it can move the jaw down, but it can probably also depress the whole head down if we keep the jaw closed instead of open like it is when it's feeding. And that is the basis of the hypothesis here, that the hyoid is helping to generate the body wave of the dolphin swimming motion. And so we see how swimmers emulate this by doing what they call the dolphin kick. And if we look at not only dolphin, but here we're looking at a blue whale, we can kind of see that S shape to the body. The head is starting to go down here. The tail is still up. And so we're seeing a bit of an S shape in here. Here is a training video. I just want to show it because it shows a person doing that dolphin kick. I want you to notice as he's teaching you how to do that, that the head is moving up and down and leading a sinusoidal wave along his body. That's really important because that is essentially what a dolphin is doing as it's swimming. It's trying to lead with its head to create a sinusoidal wave. Now, I was told that's not true. That's not what dolphins.
Oh, Joy, we lost your sound.
Okay, how about now? Am I back?
There you go. Yeah, you're back.
Yeah, I'm
Good.
sorry about that. My computer went into like screensaver mode and did
Oh.
something weird. I'm back. I'm back.
Yeah,
I'm so
by the
sorry.
way,
Okay.
since we've broken in, I'll tell you we do see your pointer, so don't worry about that.
Oh, yay. Good, good. I was concerned because it's so tiny on my screen.
It's
I
very
can barely
tiny.
see it.
Yeah, it's very
It
tiny.
is tiny. I move it a lot, so hopefully you'll see it. Okay, great. So I was told that dolphins don't move their head, that all the motion comes from their tail. But I beg to differ after looking at this video of a camera being trailed behind a boat and these dolphins swimming behind, and notice their head bobbing up and down and up and down and up and down as they swim. It's clearly a head bobbing motion that starts the whole body wave of their swimming. So when we look at a blue whale swimming, and this is a beautiful example that Tony Wu captured, and he's a really great underwater photographer of whales. He has this incredible picture here of a blue whale in exactly that sinusoidal body wave. You can see the head is starting to tip down again. The tail is tipped up, and we got a nice S shape here, which means that that downward head movement is initiating that sinusoidal body wave. So downward head movement is also important for initiating a dive, to bring the head down for a dive. So how is it that cetaceans actually depress the head? Now, when we want to depress the head, we basically are rocking it forward, but we're also using all of our neck bones to help create that curvature to go forward. That is not what happens in whales. So movement is at the joint between the skull and the neck joint. So there's a rocker bottom at the base of the skull that nests into the very first vertebra of the neck region. And that is where all the sliding motion is occurring. Everything else is fused together. So cervical or neck vertebra are labeled here as C. And like all mammals, there are 7 vertebra in the neck, 7 bones in the neck. So we've got C1 and 2, which are basically fused together, C3 and 6 through 6. And if we watch my pointer, so this is 1 and 2 together. This is C3, C4, C5, and C6. And here is C7, a little bit separated here. In some species, C7 is also adherent to C6, and it's all one big chunk. This one over here labeled T1 is the first thoracic vertebra, and you can see this spine sticking out here with this joint. This is where the first rib would attach. So we know that this is now, we're beginning the chest region here. So what we know is that in whales, the neck region is very compressed. Now, since they don't have a lot of neck flexibility because of these compressed vertebra, that motion isn't coming from the neck. It has to be coming from where the head meets the rest of the spine. So let's take a look at the spine on Betty. And I appreciate those volunteers at the top there. They're cleaning off some of these vertebra. I want you to notice the shapes of those vertebra, because we're going to talk a little bit about those vertebra, particularly these little bumps that she has her blue gloved hand sticking on over here. These bumps are going to become very important, and this one over here as well. So here's the skeleton laid out. And I've labeled C1 through 7. So you can see the little arrows going from C1, C2, C3, C4, and C5 is right next to it, really tiny. C6 and C7. This last one here is the first thoracic vertebra. And this one over here is the second thoracic vertebra. So those first 2 thoracic vertebra, they're also compressed. So we've got a lot of very flattened vertebra. And on the upper right, you can see them laid out on the table and just how flat they are. Oh, and by the way, on your website, you list these little plates as intervertebral discs. They're actually not. They're the epiphyseal plates of the growth plates on the end of each vertebra. The discs themselves have degenerated. They've decomposed. They're not there anymore. They're not ossified. But these are simply the growth plates on either side of each vertebra. So each vertebra will have one on either side like that.
Great. We'll correct it.
Okay, good. So now if we look at Betty's chest vertebra, okay, and her abdomen vertebra, okay, so the thoracic and the lumbar vertebra, we notice that they're interlocked. Remember those bumps I told you to pay attention to? Those are really important because they stabilize against lateral movement. So we've labeled C1 through 7 here. Now we've got T1 and 2, which we saw already. T3, 4, 5, 6, 7, 8, and 9 are labeled on the vertebra. And then the numbers got too fat for me to fit it on a vertebra, so I put it above. So we got 10, 11, 12, 13, and 14. 14 is broken. You can see a broken piece there. And I don't know where 15 is. Either it's this one and it's in the wrong place because its spine is too tall, or it's this one over here that's still looking for a home. Or maybe something else needs to be shifted, because when I counted the ribs, there were 15 ribs. And on this side, I counted 14 ribs, unless there's like a little piece right in there, and that might be number 15. So assuming that there's 15 vertebrae, we have to maybe add one more in here somewhere to be the last one.
One of them got broken up by the ship propeller blade, so it's in pieces.
Yeah, and that's not this one. You mean there's an additional one that's just shattered?
Yeah, there's an additional
Okay.
one.
Okay, so when you reconstruct, you may have to leave a space for that wherever that was. I'm assuming it was somewhere in the thoracic region, and that's why I only see 14 thoracics and 15 ribs.
Yep.
So just keep that in mind when you articulate. And again, I want you to look at the way these are lined up, because it so beautifully shows the interlock. You see these little flanges that stick out from each vertebra? Each one nets against the next one. So, and you can see them again over here like this, these little flanges that are sticking out. So the spine of the vertebra here is nested in between the V shape between the 2 flanges of the vertebra following it. So that interlocking means that the vertebra move easily in the up and down plane, but not so easily in the side to side plane. These are other vertebrae from other whales, not your whale, but one day you'll have it articulated like these are, hopefully even better because you'll have it mounted, not just on a shelf. But notice how each of these is interlocking. Each one of these has one of these little flanges. You can see the flanges like this interlocking with each one. So having these little flanges in here means that The vertebrae are constrained from lateral movement. They can only do up and down movement. So now we've got a constraint of a flattened neck region, and we've got limited range of motion in the whole rest of that spine. That means the whale swims very easily in the up and down motion and not so well in the side to side. And that's really important because if it were to turn its head to the side, it would present so much friction to the forward motion that it would slow the whale almost immediately. So having a fused neck stabilizes the neck, so the only joint is the rocker bottom between the back of the skull and the first neck vertebra. So there's up and down head motion. And then the whole rest of the spine is following that, in that it has up and down motion constrained by these flanges on either side. Now we add to the fact that when we look in at this, at any whale skeleton, in this case we're looking at a dolphin, we've got that hyoid bone, which was located in the front there under the jaw, with all of those attachments shown in red, blue, pink, and purple, and so on. But then we continue that row of attachments down because it doesn't end at the sternum. There's more attachments that then take over. They go across the abdomen and then go across the chest, across the abdomen, and across the tail region. And when all of those muscles are contracted, they are basically forming a continuous band or a sling, like we saw earlier on the horse diagrams, that can help bend this animal in the ventral direction. So bending ventrally in the back is easy. We've got all these big tendons that go down to the tail with these muscles, but bending in the front means that this jaw has to be closed. And when it's closed, then these muscles can pull the whole head down towards the chest. And so we end up with the downward head motion because the hyoid is stuck in the middle of that sling. So here's another diagram to show exactly what we're talking about. On the left, you see the red muscles going from the tip of the jaw to the hyoid in white, and then from there down to the chest. And on the side, we see again the muscles going from the tip of the jaw to the hyoid, and from the hyoid to the chest. And as these muscles contract, the head is pulled downward. So I'm just going to show a bit of a movie that hopefully will explain that a little better, so you can see these muscles moving and take a look at our dissection. This is from Inside Nature's Giants.
Their swimming style was already set. Unlike fish, which have a spinal movement that goes from side to side, whales propel themselves with an up and down motion. Their ancestors had turned galloping over the land into galloping through the sea. But this didn't just mean swapping legs for a tail. Joy thinks the hyoid bone she extracted yesterday from the whale's throat may hold the key to how whales swim.
Just like a human swimmer might do the dolphin kick. You know, the dolphin kick isn't just kicking your feet. You have to have a whole body wave that begins with your head and moves up and down. So the initiation, the beginning of that swimming motion must start with the head pulling down and then up. So pulling up is easy. There's lots of muscles in the back that pull the head up. But the muscles in the front, most of those are gone because these animals have to expand those huge throat pleats when they're feeding. The only thing that can really pull the head down is the muscles attached to this bone. Because the attachments, they go from the chin to this bone, in turn then go to the sternum. That's the beginning of the rib cage. And when you contract all of those muscles in a row, that means the hyoid being caught in the middle between those muscles is going to be responsible for bringing the whole head down. So if the animal keeps its jaw closed and then contracts those muscles, instead of opening the jaw, it's going to depress the head. And that's the beginning of the body wave that these animals use to swim. So that makes this bone a bone that's involved in swimming. And that's unusual because here's an animal that's locomoting with its throat.
Joy's research is turning the science of how whales swim on its head. By studying a bone crucial to communication, she unwittingly stumbled across an explanation of how they learned to swim.
So essentially what we have here is a really, really big bone that's not just big because of constraints for vocalizing or for swallowing or engulfing prey, but also for locomotion. It's all of that surface area that's necessary for all of the musculature to pull the entire huge head of this whale downward. So because the head is so big, the hyoid has to be big because it is a large structure that needs to be pulled down. And swimming is something whales do all the time. Feeding, they do intermittently, right? But swimming, they're doing all the time. So they must have a really big hyoid bone. Now, this is a picture of Betty Blue's hyoid bone. And I took this picture from my deck looking down at it because it was so big I couldn't get a good view of it except that way to get an aerial shot of it laid out on the tarp here. This is after I cleaned it off. So yay, you got it clean when you got it back. Hopefully it was degreased enough for you as well. We then wrapped it in bubble wrap and we stuffed styrofoam and boxes around the edges of it. So you can see those little cups here on either side. Stuck styrofoam all around it, padding, boxes, all kinds of little corner things, whatever. Wrapped the whole thing up in a giant box to send back. And notice I see Sheila's name there. It went back to you guys at the beginning of your Noyo Center, just starting, right? This is how
getting that box, yes.
This is how it left my house, okay? And I want you to notice, because this is really cool, okay? Do not stack heavy things on top is written on this corner. Do you see that? Do not stack heavy things on top. Do not drop or crush. Top load it with this side up. Fragile area, fragile area. Careful here, right? Because that's the middle of the bone. Top loaded. Do not stack anything heavy on it. This is how it arrived.
Yeah.
I am never, ever going to get over this. This is how it arrived. Right where it says, do not stack anything heavy on top. Of course, they did exactly that and crushed it in all the places we told it not to be crushed. However, I hope it was packed sufficiently well that it did not break. So I look forward to seeing it when it's all articulated. I want to give a very big thank you to JJ for letting me know about this blue whale and tying me in with Noyo so that I could have the specimen for the 10 years that are almost 10 years that we had it so we could get a lot of interesting data from it. Thank you to the Noyo Center for loaning it to us. I want to thank the Marine Mammal Health and Stranding Response Program for all of the specimens that we've gotten and the many students and volunteers that have helped both here and over where you are to help further our research. Funding for our work is from the Office of Naval Research and from a Prescott Stranding grant. And now I'm done. So I'm happy to take any questions.
I remember the day that box arrived and we got it, we saw it, and my stomach just went into my throat. And it arrived perfectly fine. You did such a good job packing it. The bones were fine, but it was a terrifying moment to unwrap that box.
Yep, it was. It scared me when you sent me those pictures. I was like, oh my God, I hope it's okay inside.
No, I don't know how we do it better than that, but you can't have been clearer on the box. Clearly nobody reads it. Oh my God,
Nope.
that was so fascinating. I can't believe it's like having a good meal after, 15 years of wondering, exactly what your research was. That was so interesting. Joy, thank you so much for sharing all that with us.
Oh, you're welcome.
We were just articulating a Hubb's beaked whale this fall, and we labored over the hyoid and how it should have been positioned, and I'm not sure we got it right. So I'm going to send you a picture, and you can tell me because we have to change it because we just went back and forth and back and forth and back and forth, trying to.
I'm happy to help. Send me pictures. I'll put it in Photoshop. I'll redraw where it should be if it's not already in the right place. Maybe you have it right. Maybe you have it good.
Well, we do it once, but yes, no, I think that would be great. And it's interesting to hear Mike and Michi got the hyoid a little too tucked up in there. That's so fascinating. I'll be sure to let them know that.
I think most people don't think about the hyoid. They're just like, oh, it's stuck up to the skull, but they don't think about its function and where it would be. And if the whale was swimming with its jaw closed and its head was not pulled down, it is in the right position. If it had a nice streamlined shape, like it is in most museums where it's just straight and not in an active pose, then that position's fine. But they chose a very interesting active pose, which I love. I absolutely love, but it also means things have to change.
Yeah. Well, they'll go lower, I bet. We'll tell Andrew too. So we've been talking about, and we're far from making any decisions about maybe even the sideways lunge feeding pose. So then you'll really have to tell us how that will sort of
I'll just
shift.
have to come out there and show you.
I think so. I think so. I think so. So you've been getting a lot of thank yous, and that it was a great presentation. You had far fewer questions than normal, so I think you did an excellent job covering your topic. But somebody did ask a question early on about vocalization. Can you just talk for, really briefly about vocalization, and then we can have a part two Joy talk all about vocalization.
Sure. Sure. So the larynx or voice box in baleen whales is responsible for making low frequency sounds. That's not the case in toothed whales, where the sound production is coming from the nasal region. We can talk about that another day, but basically it's an upper lip turned backwards like this and shove it into your nose. I don't know if you guys could see me on the screen there, but if you take the upper lip and you shove it into your nose like this, that's what tooth whales are doing, and that's how they're making sound. So if you try to do like a Bronx cheer or raspberry, the noise, but do it out of your nose, that's how tooth whales make their echolocation clicks. In the case of baleen whales, it's still the voice box. So if you want to make sound like a baleen whale, you've got to vibrate the larynx. Now, in us, when we make sound, you can try it yourself. You put your hand on your Adam's apple and go ah, and feel that little vibration there. That for us is lost energy. Okay, but for a whale, that's everything. It has to be able to transmit that energy out. So it has to get it into the waters. That means that the surface skin has to be loose enough to allow those vibrations to pulse like a drumhead against the water to get out. Now, what's happening with the sac is very interesting, because as they are making sounds, the air is going into that big sac. That sac can then contract and send the air back again, so they can recycle the air and do it all over again. It's also possible that the sac itself is a resonant space, or that it's the transducer, that thing that actually pulses like the drumhead to push the vibrations into the water. All of these things are still speculation. It's really hard to prove it because we don't have a baleen whale in captivity where we can see exactly what moves when they're making sound. But a lot of this is based on reconstructions, what makes sense in terms of the physics of the tissues, which parts are vibrating has been studied by people who've blown air through the larynx to see what vibrates. Again, it's somewhat artificial because an isolated voice box not in the whale is not sending the vibrations as it would in a whale's head with the other tissues, and there's all kinds of constraints with it being in air and not necessarily in a body. So we don't know for sure exactly which parts of the larynx vibrate, but there are lots of surfaces inside the larynx that have opposing structures that can vibrate as air passes between them. So we can do this in another talk, but the larynx is quite a complicated structure with lots of surfaces where vibrations can set up.
Yeah, that's so fascinating. Okay, the only other question you got is a question about that sheathing that you found on the bones. Then somebody wants to know if that's on other bones or is it just on the hyoid?
So every bone has something called a periosteum, right? Every bone.
Mhm.
And so, for example, if you get like a bruise, like someone kicks you in the shin, okay, what hurts isn't the bone. What hurts is the periosteum, because then you get blood under the periosteum and it lifts it away from the bone, and when it stretches, it hurts. That's periosteum. So we all know about it if we've ever been kicked in the shin or something similar like that. Okay, every bone has periosteum. In us, it's extremely thin, extremely thin. It's basically like cellophane on top of our bone. In most of the bones of the whales, it's pretty thin. And it's sort of like cellophane. But in some areas where there's a lot of muscle attachment, it gets really thick. So it's thick around the skull, it's thick around the hyoid bone, it's thick around a few places, the sternum. Wherever there's a lot of very strong muscle attachment, it gets thick. It's thick around the scapula, as I recall. I don't remember it being particularly thick around the vertebra, but it is thick around some of these other places. So I think it's an indication of the strength of the muscle that's pulling on that bone as to how thick that periosteum is going to be. The thickest I have ever seen it is on the hyoid. No other part of the whale has a periosteum as thick as that. So I think that that's something unique, and it
Those
speaks to
are,
the unique bone.
those are great photos. I mean, you could have said it was thick and we wouldn't have imagined that. So it was really great to show that and how thick that was. That was amazing.
Yeah,
Uh,
thanks.
so what is your next big question for your research, do you think? If you've done all this incredible sort of groundbreaking work, what's next for you?
Oh, there's always more questions. As soon as you discover something, it raises 5 more questions
Exactly.
every time. Right now, we're very interested in what the folds are doing inside the larynx of toothed whales, because if toothed whales are making sound with their nose, why did they have decorations in their larynx? It doesn't make any sense. You know, nature doesn't put decorations where they can't be seen, especially if they're going to get in the way of something like, you know, when a dolphin, for example, breathes, it breathes the way we sneeze. It's a lot of airflow all at once. So raising a delicate membrane into the middle of that airstream is setting up turbulence for no good reason. So it is my guess that there is a function. There must be. Every anatomical structure has a function, and that function might be in sound production, but it might be something else. And so we want to figure out why it looks like that. There's some other weird things going on in the toothed whale larynx that really puzzles me. It has a trabeculated surface area that looks kind of like the inside of a heart. If any of you've ever seen the inside of a heart, it looks like a mishmash of fibers going in all different directions. Now, hearts have that because they have to stretch tremendously with each beat and then contract. So, is this a diving adaptation for stretching and contracting as the animal's diving and air spaces are stretching or contracting depending on the pressure of the depth? Is this the overpressure, underpressure valve for the swimming animal? We don't know. If so, then deep diving animals like beach whales should have more of this than shallow animals. So we need to look at that a little bit further to see if that's part of the answer. But it's kind of a puzzle.
If you're collecting a larynx off a whale, how fresh does that have to be? How soon do you have to get to it?
It really depends on what we want to do with it. So if we're looking for histology to study something under the microscope, it's got to be like code 2.
Mm-hmm.
You know, I mean, code 1 is alive, if I understand right. Yeah, code 2 is like fresh dead. It has to be code 2, less than 24 hours dead. But it depends on the weather too. So if summertime, definitely less than 24 hours. Wintertime, probably get away with about 2 days before it starts to decompose. And once it starts to decompose, we really cannot do microscopic analysis anymore. It's too mushy. All the cells are lysed and falling apart. That doesn't mean we can't study other things. So we can look at the gross anatomy. We can make some predictions about where it flows and what muscles are pulling in what direction and which tissues are raised into an airstream and so on. But to really study the histology of it, to look under the microscope to see on a cellular level what's going on, we need very, very fresh tissue for that.
Okay, very interesting. All right, so you're getting a ton of thank yous. You're getting a lot of invitations to come out and visit us.
Thank you.
Mary has said the last one that said, "Dear Dr. Joy, you always wow us with your amazing knowledge of all things whales. Thank you so much for joining the Noyo Center. Please come visit. Please come visit."
I would adore doing that. I want to meet you guys in person too. I really do.
Yeah, we
Because
will
as fans.
definitely give you an invitation to the the grand opening of the laboratory when we get to that
I
point.
love that name, laboratory.
Unless anyone has any other questions, I think that sums it up. I think we've had a good anatomy lesson, a good lesson in whales, and a really interesting talk. Thank you so much, Joy. If
You're
anyone
very welcome.
has any other questions, feel free to ask now. Otherwise, we'll say goodnight. With that, have a lovely evening. I know it's getting late on the East Coast, so thanks so much. We appreciate it. We'll see you again soon, I hope.
Okay, thank you so much.
Bye-bye.
Goodbye, everyone.